Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, as you know that in one of our previous sessions we discussed on one of the biomolecules, that is carbohydrates. Today also we are going to conduct a in-depth analysis on carbohydrates, and today we are going to discuss some reactions and rearrangements in carbohydrates chemistry, as well as we are going to discuss on Fisher's proof for determination of configuration of glucose. And for this, dear friends, we have again with us in our studios Dr. K.K. Arora. Dr. K.K. Arora is Associate Professor in Department of Chemistry, Zakir Hussain, Delhi College. So, dear friends, let's welcome our guest, Dr. K.K. Arora, and let's try to understand more about carbohydrates. Hello, sir. Welcome to the EduSet lecture. So, over to you, sir.
Hello, friends. In our previous session on carbohydrates, we had discussed some reactions which led to structure for glucose and fructose. Both are naturally occurring monosaccharides. Today, we are going to discuss some important reactions and rearrangements which we come across in carbohydrate chemistry. So, first we will briefly revise what we had done in our previous session, and then we will talk about epimers and the process of epimerization. Then we shall take up the base catalyzed rearrangement of aldoses and ketoses. We will talk about the Osazone formation, which are important derivatives of carbohydrates. We will take up the method for increasing the chain length as well as for decreasing the chain length. Then we will talk about the methods for conversion of aldose into ketose and a ketose into aldose. We will discuss then Fisher proof by which the configuration of D plus glucose was determined, and based on this proof how the configuration of D minus fructose was established, and finally we will summarize our today's work. So, in our previous session we discussed that carbohydrates are naturally occurring biomolecules, and chemically they are defined that they are polyhydroxy aldehydes or ketones or substances which give such units on hydrolysis. Means these are the compounds which have hydroxyl groups as well as some aldehyde or ketonic functional group, and based on this definition they are classified as monosaccharide, disaccharides, oligosaccharides and then polysaccharides. Disaccharide means which give 2 monosaccharide units on hydrolysis, and oligosaccharide means which give between 2 to 10 monosaccharide units on hydrolysis. Monosaccharides are those which cannot be further hydrolyzed to give simpler units of polyhydroxy aldehyde and ketones, and their examples are glucose, fructose, ribose, etc. Whereas the compounds which come under oligosaccharides, as I said, they give 2 or more than 2, but up to 10 monosaccharide units. The most common examples are sucrose, maltose, lactose, etc. And polysaccharides are those substances which give more than 10, generally we call it as a large number of monosaccharide units on hydrolysis, and the common examples are starch, cellulose, glycogen, etc. Then they can also be classified on the basis of functional group in them. If they have got an aldehydic functional group like this, then they are classified as aldoses or aldose sugars, and if they have got a ketonic functional group, then they are called as ketoses or ketose sugars. They are also classified on the basis of their reaction with tolerance reagents or Felling reagents, and they are classified as reducing sugars or non-reducing sugars. Those sugars which reduce the Felling solution and tolerance reagents, they are called reducing sugars, and which do not react with them, they are called non-reducing sugars. All monosaccharides are reducing sugars, whereas some of the disaccharides are reducing. So, non-reducing sugar means they do not have free aldehydic or ketonic group. But one thing you have studied in the chemistry of aldehydes or ketones, that we differentiate between aldehyde and ketone on the basis of these two reagents. compounds which give the positive test with test, tolerance reagent or Fehling solution, they are generally aldehyde groups, and which do not react with these, they are ketones. But here monosaccharides, whether they have got aldehydic functional group or ketonic functional group, if the functional group is free, then they reduce these both the reagents and we call them as reducing sugars. We will discuss the reason later that why they give both the tests. Then based on certain reactions which we have discussed in our previous session, glucose and fructose were assigned the open chain structures like this. This was the structure up to which we arrived for glucose, that it is a 6 carbon compound with one aldehyde functional group, 6 carbons in chain, each carbon having one hydroxyl group, and this compound overall has got 5 hydroxyl group and 1 oxygen as aldehydic functional group. So, it is an aldohexose, whereas fructose was found to be compound having one ketonic functional group, 5 hydroxyl group, all 6 carbon in straight chain. So, this was a ketohexose. Based on this structure, we said that this structure has got 4 asymmetric carbon atoms. This carbon which is written as 4 here, CHOH 4 times, these all 4 carbons are asymmetric. So, it means 16 isomers are possible for this particular structure, 16 configurations are possible, and out of those 16, it is only one configuration that represents plus glucose. In case of fructose, there are 3 asymmetric carbon atoms. So, 8 isomers are possible, and out of those 8, it is one that actually represents the minus fructose. We will discuss today the proof that was given by Fischer for configuration of these two compounds. But before going into that, this is the configuration that was given by Fischer, because I will be using it during some reactions. How this configuration was arrived at, we will discuss a little later. This configuration that was given by Fischer has got hydroxyl on the carbon 2 on the right side, on carbon number 3 towards the left side, and carbon number 4 and 5 on the right side. This is written in the Fischer's projection. Fructose was found to have a similar configuration at carbon number 3, 4 and 5. That is, at carbon number 4 and 5, the hydroxyls are placed on the right side, whereas on carbon number 3, this hydroxyl is placed on the left side. Carbon number 2 is carbonyl, so it is not asymmetric, and carbon number 1 has got 2 hydrogens attached to it, is also not asymmetric. Now, when a molecule has got one asymmetric carbon atom, then its mirror image is non-superimposable over it. This is what you know from your study of stereochemistry. And a compound, and when its mirror image are non-superimposable, then such a pair of compounds, they are called enantiomers. If a compound has got more than one asymmetric carbon atom, then number of isomers is more than 2, and these isomers have one more relation, they are called diastereoisomers. Diastereoisomers are those isomers which do not have mirror image relationship with each other. Enantiomers are those isomers which are non-superimposable mirror image of each other. Now, if we look at this configuration for plus glucose, where 4 asymmetric carbon atoms are there, then its mirror image, that will be for obviously for minus glucose, the two isomers will differ in their configuration at all the 4 asymmetric carbon atoms, that is carbon number 2, 3, 4 and 5, it will be the mirror image here. But suppose we have another isomer with this molecular formula which differ in the configuration only at one carbon, any of these one carbon, then a new term is used in carbohydrates. Such isomers are called epimers, that is those monosaccharides which differ in their configuration at any one of the carbon atoms, they are called epimers, but at which carbon they have different configuration, we have to mention that carbon, such as if they differ at carbon number 2, then we will call them as C2 epimers. If they differ in their configuration at carbon number 3, we call them as C3 epimers. But in general, in case of aldoses, we do not mention the number of carbon if they differ in their configuration at carbon number 2. For example, this is the configuration of D-mannose. As I told you that how these configurations have been arrived, we will discuss it little later. For these purposes, the configurations are being used which were obtained by Fischer's proof. This is the configuration for D-mannose and this is the configuration for D-glucose. What we find that they have a similar configuration at carbon number 3, 4 and 5 both. Lower 2 hydroxyls are placed on the right, this hydroxyl is placed on the left. Where do they differ? They differ in the configuration at carbon number 2 only. In glucose it is on the right side, whereas in mannose it is on the left side. So, glucose and mannose, they are epimers. Since they differ in their configuration at carbon number 2 only, so as I said before that when the configuration is different at carbon number 2, then we may not mention it and we may simply call as epimers, but more specifically we may call them as C2 epimers. Let us compare the configuration of this D-glucose with D-galactose. What we find that the configuration of carbon number 2 it is same, carbon number 3 it is same, in both the cases hydroxyl is on the left, but they differ in their configuration at carbon number 4. In galactose this hydroxyl is placed on the left side, whereas in glucose this hydroxyl is placed on the right side, and again at carbon number 5 they have the identical configuration. So, it means these two compounds they differ in their configuration at carbon number 4. So, they are again epimers, but here we will have to mention that they are C4 epimers. So, if they differ in the configuration at carbon number 2, we call them as C2 epimers or only epimers, and if they differ in configuration at any other carbon, then we mention, such as here they are called C4 epimers. Then how the epimers can be converted into other one? We call this process as epimerization. For example, this is an aldohexose, although we have written it for glucose only, but in general we are saying this is an aldohexose. We want to obtain its epimer, means compound with the configuration that will differ at this carbon only, the opposite configuration. So, sequence of reaction is used for it and it involves the oxidation with bromine water, and we had discussed earlier that it is the aldehyde group that gets oxidized by bromine water. We get this monocarboxylic acid. Then this carboxylic acid is treated with pyridine. Now, pyridine is a base, and what happens? A equilibrium product is formed, these two products remain in equilibrium and the configuration on this carbon has changed. This hydroxyl which were on left side has come on the this was on right side, has come on the left side. Now, how this happens, this I will take after this. This is the rearrangement that occurs in alkaline medium. Pyridine is a base, so this rearrangement occurs and we get an equilibrium mixture of the two. Then it is heated and a water molecule is lost. Now, on the loss of water molecule, what happens? Actually, an ester is formed between this carboxylic group and one of the hydroxyl from the chain. It is generally this hydroxyl of the carbon number 4 which involves a cyclic ester which are known as lactones. This OH of the acid and OH of this alcoholic part, they lose a water molecule and cyclic ester is formed. So, this is the cyclic ester which is being formed. Now, this cyclic ester will be formed from this as well as from this isomer both. Here we have shown from this isomer, but obviously the another lactone will be there from this isomer also. Then on reduction with sodium amalgam, this ester bond breaks, one hydrogen goes with this carbon, one hydrogen goes with this oxygen. So, it becomes back OH and this becomes CHO, that is aldehyde. So, now we have obtained another aldohexose in which the hydroxyl is on the left hand side. So, I will repeat briefly that in epimerization what happens? We start with one aldohexose, it is oxidized to corresponding monocarboxylic acid, that is aldonic acid. Then it is treated with pyridine, where a rearrangement occurs, which I am going to discuss just after it, that how it happens, and we get an equilibrium mixture of two epimeric carboxylic acids, which on heating will obviously give a mixture of epimeric lactone, and then this on reduction will give both the aldohexose, that is starting one and the epimeric isomers. So, this is the process of epimerization. Now, next let us take up that how this rearrangement occurs in alkaline medium. The same rearrangement gives us the answer of the question that why ketonic compounds, that is ketohexoses, they give tolerance test as well as Fehling test. Remember that both these tests, tolerance test as well as Fehling test, they involve the alkaline medium. So, what happens? The ketose sugars also in this alkaline medium, they undergo the rearrangement. This rearrangement was given by Lobry de Bruyn and van Akenstein, and it is known as the same by the name of both the scientists. We also call it as Lobry de Bruyn van Akenstein rearrangement. Now, in presence of alkali, what actually happens? This is any aldose. We are using just top two carbons. Obviously, there is a chain of carbon under it. Now, when the carbon number 2, a base abstracts this hydrogen, the pair of electron shifts here and this pair of electron goes here to this oxygen. This is a keto-enol tautomerism, right. So, this oxygen will capture H from the solvent and it will become OH. So, now it has become enol and this was here keto. So, this in alkaline medium, the keto form has been converted into the enol form, but there is another hydroxyl which is already there. So, we call it as enediol, this en for this double bond and one hydroxyl here and one hydroxyl here. So, enediol is being formed. Now, what happens? If this enediol, this hydrogen is now captured by the alkali, this pair of electron will shift here, this will go there and this carbon will capture H and we will get the keto form, but this is different from the starting one. What had happened? Actually, both are hydroxyl. Now, if this base abstracts the hydrogen from here, then we will get the starting compound, but if the base abstracts hydrogen from here, we have obtained another keto form. And similarly, if this base captures back the hydrogen, then it can capture on the two faces, because once this carbon carbon double bond is formed, now this carbon is sp2 hybridized, it is planar. The hydrogen can come from the same face, then we will get the starting aldose, but if it comes from the other phase, then we will get the epimeric aldose. So, what happens? We start from one aldose, treated with alkali for some time, we will end up with an equilibrium mixture of epimeric aldose as well as corresponding ketose, plus there may be some other products also. Similarly, if we start from this ketose, then in alkaline medium, first this hydrogen will be taken up, the pair of electron shifts here, this becomes OH, we get enediol, enediol may be converted into this aldose or this aldose. So, what happens? If we have a ketose sugar and treat it with some alkali, we are getting a mixture which has got some aldoses also, and actually these aldoses now they react with the tolerance reagent or Fehling's reagent, and this is the reason that ketose sugars also give these two tests and they are also categorized as reducing sugars. since we start with any of the aldoses, this one we will get epimeric, or we will start with this one, then obviously this is its epimer, this is the corresponding ketose sugar, and all these mixtures of compound, they exist together after some time. And that is why the properties or reactions which are studied in alkaline medium will give all sorts of reaction which are given by aldose or ketose. Now, let us explain that how it got converted into the epimer, although there I showed using the 2 carbons, here I have taken a specific example. This is D-glucose with its configuration, and specifically the configuration has been shown at this carbon in wedge and dash structure. This base captures this hydrogen, this pair of electron goes here, this carbon now becomes double bond, and this pair of electron goes to this oxygen. And when this electron pair comes back, and these pi electrons, they capture hydrogen back from the water, hydrogen can come on the same phase, we will get the starting, that is D-glucose. If it goes on the opposite phase, that is hydrogen on this side, then hydroxy will be here, we get D-mannose. So, if I start with glucose, we are getting the mannose. Obviously, we will get the corresponding keto sugar also, but these 2 steps they show that how one aldose gets converted into its epimeric aldose. Then how, if we start with the ketose sugar, then how do we get aldoses? This is fructose, this is C double bond O. If a base captures a hydrogen from here, the first carbon, then the pair of electron will shift here, and this pi electron between CO will shift to oxygen. So, this becomes OH and this becomes C double bond C, and here it is basically the enol form that could be obtained from D fructose, or we obtain the same enol from D glucose, or the same enol will be obtained from D mannose. And then alkali captures hydrogen from here, this pair of electron shifts here, and this gets converted into aldehyde group, and we will get a mixture of D glucose and D mannose. So, ultimately we start from any of these compound, after some time on keeping in alkali, mixture of all these compounds will be there. Then there are one important derivatives of glucose or other monosaccharides, we call them as Osazone, and some disaccharides also give these Osazone derivatives. We know that carbonyl compounds, that is aldehyde or ketones, they react with phenylhydrazine to form a type of derivatives which are called phenylhydrazones. Here it is shown, any carbonyl compound, whether this is cyclohexane has been shown, but it may be cyclohexanone or any other ketone or aldehyde will react with one molecule of phenylhydrazine, a water molecule is lost, and we get these derivatives which are called phenylhydrazones. But when this phenylhydrazine is treated with a glucose molecule, then actually 3 molecules of phenylhydrazine are consumed, and rather all monosaccharides they react with 3 molecules of phenylhydrazine to give a derivative which are called osazones. So, D glucose gives this compound as osazone, where 2 phenylhydrazine molecules are attached in the molecule, and configuration at remaining 3 carbons it remains same. So, we will discuss that how this carbon which is having actually OH group, alcoholic group, is forming this C double bond N. Then when the fructose was taken, D fructose, and when it is treated with phenylhydrazine, again a osazone is obtained, and that was identical that was obtained from glucose. So, that is why this osazone may be called as glucosazone or fructosazone. Now, how these osazones are formed? Again I have taken a aldohexose glucose, and since reaction occurs at 2 carbons only, so we are showing these 2 carbons for the simplicity, that first this aldehydic carbon reacts with phenylhydrazine to give this phenylhydrazone here, this carbon, this CH and OH are like this. This carbon has got one H and one OH. Now, what happens? This pair of electron shifts here, H is lost as H plus. Actually, it is not lost as H plus, it is captured by this nitrogen, because when this pi bond is formed here, these pi electrons they move and they form the bond between this N and H. So, basically what has happened, from the imine it has been converted into this C double bond C and amine here, the H goes here. So, this is also a tautomerism. Then this equilibrates and can be written like this. This is COH, this is now CH, single bond N and one hydrogen has gone to this nitrogen. So, it has become CHNH, it is next NH and then pH, and this hydrogen which is attached to oxygen and this nitrogen, they form a intramolecular hydrogen bonding here, and we get a 6-membered cyclic structure. Next, what happens? Again a rearrangement occurs here, this pi electron shift there, this bond between two nitrogens it breaks, and these electrons come here and form a sigma bond with this hydrogen, and this OH bond breaks and this pair of electron shifts here. So, what actually happens? This portion of the molecule pH NH2 is lost as molecule of aniline. This becomes C double bond O and this becomes CH double bond NH. So, one molecule of aniline is lost and we get this CH double bond NH, C double bond O. Now, this reacts with another molecule of phenylhydrazine and this CO is converted into phenylhydrazone here, and then it reacts with another molecule of phenylhydrazine. This is lost as ammonia and we get CH double bond and NHPH here. So, two molecules of phenylhydrazine are now attached to carbon number 1 and 2 and the product is called Osazone. Since this Osazone is obtained from glucose, we call it as glucosazone. Then from fructose, that is when carbonyl group is at carbon number 2, similar type of reaction, sequence of reaction occurs. It reacts with one molecule of phenylhydrazine, first a hydrogen is formed here, then similarly this H changes its position, it goes to this nitrogen and this pair of electron comes here and we get this structure, which is now this nitrogen is hydrogen bonded to hydrogen from this OH group. Then this is lost as a molecule of aniline, this bond is cleaved, this pair of electron shifts here and this pair of electron goes there, and again we get C double bond NH and C double bond O. So, we get this structure. Again now it reacts with a second molecule of phenylhydrazine, this is converted into phenylhydrazone and then this also reacts with another molecule of phenylhydrazine giving this Osazone, we call it fructosazone. Now, in both these cases we have seen that it is carbon number 1 and 2 reacts. Why this oxidation does not occur to the next carbon? Because once this is formed, a similar reaction can occur to the next carbon, which is also CHOH. Reason for this has been given as once this type of structure is formed, then it is stabilized by hydrogen bond formation and we get this stabilization here. This is CH and C, first and second carbon here, indicating C double bond N, NHPH, C double bond N, NHPH. It is either this hydrogen may form hydrogen bond with this nitrogen, or it is this hydrogen may form hydrogen bond with this nitrogen, or both of these 6-membered intramolecularly hydrogen bonding structure they exist, they get stabilized and further reaction does not proceed to third carbon. So, this is about the Osazone formation. Next, we take up the method for increasing the chain. Whenever we carry out any conversions and if we want to prepare a higher homologue of an aldose from a lower homologue, that is we want to increase the chain length by 1 carbon, then one of the most common reaction which is used is Killiani-Fischer synthesis. Again for the reaction I have shown here only the first 2 carbons, obviously under this bond there is the remaining part of the monosaccharide. In the first step, addition of HCN is carried out. So, HCN you know it adds across this carbonyl group to form cyanohydrins, and directly HCN is actually not used. We use KCN or NaCN in presence of some mineral acid like hydrochloric acid as a reagent here. After the addition of HCN, we get now this cyanohydrin, but in the formation of cyanohydrin, what has happened? Two things happen. One, cyanide group adds, means one carbon is increased in the chain length. Second, this C double bond O of the aldehyde, which was earlier sp2 hybridized carbon, when H goes to this oxygen and CN goes to carbon, C double bond O breaks, and this carbon now becomes sp3 hybridized carbon, and this carbon is also now asymmetric carbon atom. It has got one hydrogen, one hydroxyl, one cyano and one remaining part of the molecule. So, if it is an asymmetric carbon atom, obviously two isomers will be formed. So, whenever after the addition of HCN cyanohydrin will be formed, we will have mixture of two isomers, that I will show in the next slide. Then this cyanide is hydrolyzed with mild base like barium hydroxide and then acidified. The CN gets oxidized into carboxyl group. Obviously, we will have mixture of two carboxylic acids. Then this carboxylic acid is heated and corresponding lactone is formed. As we discussed in a previous reaction also, in epimerization, a cyclic ester, that is a lactone, is formed. This lactone is reduced by sodium amalgam. This bond breaks here, this goes as OH on this carbon and this becomes as aldehyde, H comes here. So, we will end up now the product which has got one more carbon than the starting compound. I have not shown the lower part, whatsoever the carbon were there, that part is here, but it was 2 carbon portion here, now we have 3 carbon portion here. So, this is aldehyde, this is the another carbon which was earlier aldehyde, has now become CHOH and it is now asymmetric carbon atom, and here we are having mixture of 2 isomers. So, in a Kiliani-Fischer synthesis, we will always get mixture of 2 higher aldoses which differ in their configuration at carbon number 2, and we discussed before that such aldoses which differ in configuration at carbon number 2 are called C2 epimers or simply epimers. So, Kiliani-Fischer synthesis always leads to the formation of epimers. Let us take the example. Suppose it is D-arabinose, it is a 5 carbon sugar. So, I have shown this in a box that no configuration change occurs here. HCN adds on to this aldehyde group, and here we will get 2 isomers. In one case hydroxyl is placed on the right, in another case hydroxyl is placed on the left, and then this cyano will be ultimately hydrolyzed to carboxyl, cyclic ester and then converting back into aldehyde. So, we will get mixture of epimers. This is the full reaction that shows from an aldopentose that first step is addition of HCN, we will get mixture of 2 cyanides, they are hydrolyzed, we will get mixture of 2 acids. Then on heating they lose water molecule, we get mixture of 2 lactones, and then on reduction we will get mixture of 2 epimeric aldehydes, means they will have identical configuration at the lower asymmetric carbon atom. They will differ only in the configuration which is newly formed, and that newly formed carbon is the one which was present in our starting compound as aldehyde group. This CHO is basically now this CHOH on this side or on this side, and the CN that has been added is in the form of this CHO. This Kiliani-Fischer synthesis has now also been modified and it has been slightly simplified also. And in this modified method, what is actually done, that oxidation to carboxylic acid is not carried out. After the addition of HCN, we get this mixture of 2 epimeric cyanides. They are reduced partially using palladium and barium sulfate, and this is partially reduced to CH double bond NH, that is we get imines. So, cyanides are partially reduced to imines. If we carry out complete reduction, they will be converted into primary amines, but this barium sulfate acts as a catalyst poison and partial reduction occurs to imines, and then these imines on hydrolysis give the corresponding aldehyde. So, steps are reduced, that first we were oxidizing earlier into carboxylic acid, then esters and then reduction. Here cyanides are directly partially reduced and then hydrolyzed. Then the method by which we can reduce the chain length by one carbon, and one of the most important method which is used is Ruff's degradation. In Ruff's degradation, say this is D-glucose, first it is oxidized with bromine water, this aldehyde will be oxidized into carboxylic acid, and then it is treated with calcium hydroxide to form the calcium salt. Calcium has got 2 valencies, so here it is calcium 2 plus and half is written because one calcium ion here will form the salt with 2 these glucaric acid molecules, gluconic acid molecules. So, we call this molecule as calcium D-gluconate also. And these calcium salts of this monocarboxylic acid from aldose on oxidation with this reagent, which is hydrogen peroxide in presence of ferric ions, and this oxidizing reagent is also named as Fenton's reagent. So, it oxidizes in such a way that this carboxylate anion portion is lost as carbon dioxide and next carbon gets oxidized into the aldehyde group. So, in one sequence of reaction only one carbon is lost. So, this method for reducing this chain length is also very specific, and we get the lower homologue of any aldose sugar in which chain length is reduced by one carbon. Now, in all these reactions, whether it was epimerization or converge increasing the chain length or decreasing the chain length, we have seen that all these reactions are carried out on aldoses. Suppose we want to do any such reaction on ketose, then what? For that, what we will have to do, first ketose is converted into aldose, then we carry out this reaction, and then aldose is converted back into ketose. So, how to convert an aldose sugar into a ketose sugar? So, this is a 2 carbon portion again shown from any aldose. In the first step, we prepare the Osazone, that is treated with excess of phenylhydrazine, and we get the Osazone. Suppose it is glucose, then we get glucosazone. Then this Osazone is hydrolyzed, and what will happen, this CH double bond NH portion and then C double bond, and these 2 portion will be hydrolyzed, and we will get C double bond O here and C double bond O here. These molecules are called ozones. This is an aldehydic carbon, this is a ketonic carbon. Now, if we reduced with those reagents where aldehydes can be reduced, such as zinc and acetic acid, then this will be reduced into primary alcoholic group, that is CH2OH, and this will remain as C double bond O. So, we get a ketose sugar. So, from aldose sugar we can convert it into ketose sugar by this sequence of steps, that first prepare the Osazone, then hydrolyze and then reduce the aldehyde group into primary alcohol. Now, when we want to convert a ketose into an aldose, this is a ketose sugar, 3 carbon portion has been shown. This is C double bond O is first reduced into alcoholic portion using hydrogen and nickel. So, we get now this alcohol, and obviously it will be, since this carbon is now becoming asymmetric carbon atom, we will get mixture of epimeric alcohols. Then this mixture of epimeric alcohols on oxidation with nitric acid, primary alcohol part will be converted into carboxylic acid. This will be again mixture of epimeric acid. Then this acid is heated to give the lactone, a water molecule is lost. Again this lactone will also be a mixture of compound, then this is reduced, this CHO is formed here after this bond is cleaved, and this is now CHOH. So, here where CO was there, it has now become CHOH, where CH2OH was there, it has now become CHO. So, ketose has been converted into aldose, but aldose we will never get a single compound, we will get always a mixture of epimeric compounds here. And second thing, here I have shown the oxidation of this primary alcohol only. obviously when it is a chain length of 5 or 6 carbon, the lowermost carbon in the ketone sugar is also a primary alcohol that would also be oxidized into carboxylic acid, that will also form the ester and ultimately will give an aldose. So, we will end up with mixture of aldoses. So, this is not a very good method for conversion of ketose into aldose, but out of the many products formed, one of them obviously will be there which is required. Now, we come to the configuration of D plus glucose. As I said, this configuration was established by Fischer and we call it as a Fischer proof for assigning this configuration. I discussed earlier that this open chain structure for glucose was given on the basis of certain reactions, where we said there are 4 asymmetric carbon atoms, 16 isomers are possible. Now, out of those 16 isomers or 16 configuration, the one that represents D plus glucose, this work was done by Emil Fischer, and the work which I am going to discuss in next 10 minutes by giving 4 or 5 reaction, it took Fischer 4 years. He started this work in 1888 and he reported the actual configuration for D plus glucose in 1892, and you can understand the importance of this work at that time, that for this work he was awarded the Nobel Prize in 1902. So, he studied many reactions and he prepared all the 16 isomers starting from glyceraldehyde, rather starting from both the isomers of glyceraldehyde and carrying out Kleene-Fischer synthesis, and every time getting 2 isomers and then carrying out the further Kleene-Fischer synthesis, so that he had the samples of all the 16 isomers with him. But the problem was that which isomer has got which configuration, that was not known at that time, and he worked after studying number of reactions. As I said earlier, I will be discussing here only those reactions which gave a direct evidence towards the configuration of D plus glucose. So, let us take up these evidences one by one. For assigning the configuration, obviously out of 16, Fischer chose those 8 isomers where this configuration for the lowermost asymmetric carbon atom was fixed and hydroxyl was taken towards the right side. This was arbitrarily taken at that time on the basis that the D plus glucose, rather I will say plus glucose, was correlated with the plus glyceraldehyde, and that is why it was assigned the configuration D. And for plus glyceraldehyde, arbitrarily it was said that hydroxyl is on the right side, although at that time there is no evidence at that time, and this configuration was established after about period of 60 years, somewhere in 1950, when many instrumentation were developed and the configuration was established that it is true that hydroxyl in plus glyceraldehyde and all the compounds which were correlated with it is on the right side. So, he placed the 16 out of the 16 8 configuration by fixing the configuration at one of the asymmetric carbon atom to be fixed on the right side. He took first configuration when he placed all the hydroxyl on the right, and then second its epimer when hydroxyl at carbon number 2 is placed on the left. Then 3 when the hydroxyl on the carbon number 3 is placed on the left, 2 others on the right, and then its epimer where the configuration of 2 is also on the left. So, 2 3 both on left, here 3 on the left. So, 3 and 4 forms an epimeric pair, 1 and 2 are epimeric pair. Then 5th where the configuration at carbon number 4 was placed on the left, then its epimer where configuration of position of hydroxyl at carbon number 2 and 4 was placed on the left side. Then configuration in which these 2 hydroxyl at carbon number 3 and 4 they are placed on the left side, and then its epimer when the hydroxyl on the carbon number 2 is also placed on the left side. So, 1 2 3 4 5 6 7 and 8 they are written in such a way, so that are representing epimeric pairs. Then as I said before that plus glucose was obtained by the Cleany-Fisher synthesis of minus arabinose. So, it means we should have the configuration for minus arabinose also, and keeping the same argument, that is keeping this hydroxyl or the lowermost asymmetric carbonate on the right, he write the 4 possible configurations for minus arabinose, which could be correlated with D-glyceraldehyde. So, I will say D minus arabinose, that these 2 hydroxyls on the right, then its epimer, this hydroxyl at carbon number 2 on the left, then the hydroxyl at carbon number 3 on the left, and its epimer when 2 and 3 both are on the left. Obviously, 4 other isomers will be those in which this hydroxyl will be on the left hand side. These were here given the, these are given the numbers 9, 10, 11, 12. Now, the evidence. The first evidence goes like this, that on oxidation minus arabinose gives an optically active dicarboxylic acid. Means it was observed experimentally that minus arabinose, when it is oxidized, the dicarboxylic acid which is obtained is optically active, and based on this we can say that as the configuration for this carbon is fixed, we are keeping it on the right. If this acid, the dicarboxylic acid which is to be obtained, will be obtained by the oxidation of this aldehyde into carboxyl and this lower primary alcohol into carboxyl. Whatsoever is the position of hydroxyl on this carbon, if this hydroxyl is on the right side, then we will end up with a meso compound, and that will be optically inactive. Means the position of the hydroxyl at carbon number 2 has to be on the left side, and at 3 it may be left or right side. So, the possible formulas which we have written earlier, this 10 and 12, they represent this partial formula. So, configuration for minus arabinose can be 10 or 12, it cannot be 9 or 11. I will show about 9 and 11 also. This is 9. When these 3 hydroxyls on the right side, when this is oxidized, we will get this dicarboxylic acid, and this is a meso compound. It has got a plane of symmetry here, it will be optically inactive. It means minus arabinose cannot be 9. Then this is the configuration 11. When this is oxidized, again we will get the dicarboxylic acid which has got a plane of symmetry here, and this is a meso compound, will be optically inactive. So, even 11 cannot be minus arabinose. So, out of these 4 possible configurations for minus arabinose, 9 is not possible and 11 is not possible. So, we are left with 10 or 12 possible configurations for minus arabinose. Then next evidence, we know that minus arabinose on Cleany-Fisher synthesis gives a mixture of plus glucose and its epimer plus mannose. So, they should have the same configuration about C3, C4 and C5 as in case of minus arabinose. I discussed before in Cleany-Fisher synthesis that the CHO group which is there, that becomes the epimeric carbon now, and there we get the 2 isomers. So, configuration at the lower 3 carbons, it should not be disturbed, it remains the same. So, it means that we have already deleted 2 possible configurations for minus arabinose, and based on that we can delete some configurations for glucose and mannose also, because glucose and mannose both are obtained in the same step, they are epimer. So, if 10 or 12 are the possible configuration for minus arabinose, and now this carbon becomes the epimeric carbon. So, it will be hydroxyl on the right or hydroxyl on the left. So, only those configuration for glucose mannose pair are possible which have hydroxyl at carbon number 2 on the right or left, and on 3 only left, because on carbon number 5 we have already fixed the configuration to be hydroxyl on right side. So, out of these possible 8 configurations now, 1 cannot be the configuration for this glucose or mannose, because they represent the glucose mannose pair, they are epimers here. Since this is not the possible configuration for minus arabinose, 1 and 2 cannot be glucose mannose pair. Similarly, 11 cannot be the configuration for minus arabinose, 5 and 6 cannot form the glucose mannose pair. So, we are left now with 4 possible configurations, and again it in the form of pair, either 3 and 4 represent glucose mannose pair or 7 and 8 represent glucose mannose pair. Then next proof, both glucose and plus mannose on oxidation give optically active dicarboxylic acid. Means when the oxidation of plus glucose or plus mannose was carried out, and the dicarboxylic acid which is formed is optically active. Now, let us see here, if configuration 3 is for glucose or mannose, any of the two, this on oxidation will give this dicarboxylic acid, and this will be optically active because it has got no plane of symmetry in it. And if this is the configuration whether for glucose or mannose, this on oxidation will give this dicarboxylic acid, this will also be optically active because it has got no plane of symmetry. It means according to this evidence, a pair of 3 and 4 may represent glucose mannose pair. Let us talk about this 7 and 8. The 7 configuration that we have written, when this will be oxidized, we will get this dicarboxylic acid, and this is a meso compound, has got plane of symmetry here. This is optically inactive. Although the configuration 8, this on oxidation gives this dicarboxylic acid which will be optically active, but we know that it is a pair either 3,4 or 7,8 representing glucose mannose, and both of them are giving optically active dicarboxylic acid. So, it means these two 7 and 8 cannot represent the glucose mannose pair. So, obviously, we are left with the configuration either 3 or 4 for glucose and 3,4 representing glucose mannose pair. So, we delete these also, and now we are left with these two configuration. So, if these two are not the configuration for glucose mannose pair, and we know that glucose mannose are obtained from minus arabinose, so minus arabinose also cannot have this configuration. So, we are left with only one configuration, that is 10 for minus arabinose. Then we are now left with one thing only, that out of 3 and 4 which represents plus glucose, and this was decided on the basis of another reaction, that the dicarboxylic acid obtained from plus glucose was obtained by the oxidation of one more aldohexose, that was named as plus gulose. As I said before, that Fischer had prepared all the 16 isomers and he oxidized all of them. He found that the dicarboxylic acid that we are getting from plus glucose, the same dicarboxylic acid is obtained from one more aldose sugar. So, if we look at the configurations which we had written earlier, we can see that it is the enantiomer of 5. It is written in the inverted way, but it is enantiomer of 5 that on oxidation will give the same dicarboxylic acid which is obtained by the oxidation of plus glucose. If configuration is 3, this is the configuration number 3. So, the dicarboxylic acid that is obtained from 3 is obtained from the enantiomer of 5, but the dicarboxylic acid obtained from this configuration number 4, this dicarboxylic acid cannot be obtained by any other possible configuration. It could be obtained only if it is 4 is written in the inverted form. So, it means that if configuration number 3 cannot be obtained by this 4 cannot be obtained by any other configuration that is written, it means that is representing mannose and 3 is representing glucose. So, based on this we say that glucose has got this configuration and this is not the configuration for glucose, obviously it will be for mannose. So, based on these sequence of steps which I have discussed and which give direct evidence towards the configuration of D plus glucose, this configuration was established. Based on this, the configuration for other monosaccharide was given. We have discussed earlier that number 10 configuration represents minus arabinose, number 4 configuration it represents plus mannose, and we said that it was the oxidation of one of the isomer, that was the mirror image of 5, that gave the same dicarboxylic acid that was obtained by the oxidation of 3. So, this configuration 5 represents minus glucose. Now, based on all this, then the configuration of fructose was also established. We have discussed earlier that it is the same Osazone which is obtained from D plus glucose or D minus fructose. Since they give the same Osazone and formation of Osazone involves only the carbon number 1 and 2. It means this carbon number 3, 4 and 5 in both glucose as well as in fructose have got the same configuration. So, based on this, this configuration is given to D minus fructose. So, this is the Fischer's proof by which the configuration for D plus glucose was established, then D minus fructose was established, and many other monosaccharides, their configuration was established. So, we will stop here today, and in our next session we will talk about the cyclic structure of these monosaccharides. Till now we have been talking about their open structure only. These are the open chain structures, and actually they do not have these open chain structures, they have a cyclic structure. On what reactions these cyclic structures were established, that we will take up in our next session. Thank you.
With this note, thank you sir, thank you so very much. As Dr. K.K. Arora himself said that we would be covering the cyclic structure in our forthcoming sessions, and we would be discussing more on carbohydrates. Till then, dear friends, we say goodbye to you, but we would be meeting again very soon. Till then, if you want to access this lecture, then I want to tell you all that very soon we are going to upload this lecture on YouTube, with the help of which you can access it. And if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in. We would be meeting again. Till then, take care. Goodbye. Thank you, sir. Thank you so very much.